So, what's up, guys? This is again your resident chemistry tutor, Mark. And before anything else, I would like to sincerely apologize for the really bad audio quality of a majority of a major part of my video. It's because that the noise canceling headphone that I use to record my voice in this video is also really crappy. So, amo na nga daw medyo may sagra ka mga mabatian sa background, and I can't cancel it out even if I edit it using audio editing software apps. So I hope that you'll find this video educational despite the technical difficulties that we will be encountering here. And once again, I'm really sorry. Now, the topic that we will be discussing for this video will be on how to express the concentration of a solute in a solution.
So the units of concentration that we will be discussing in this lecture will be parts per percent mass. So everything, basically everything that is included in your in the week 8 of your module, but we will skip the part for the mole fraction since it has been discussed in gases, as I've which is already included in our previous video tutorial. I will also include a new unit of expressing concentration, which is parts per billion, which is just basically an extension of your parts per million. Okay, so let's start. So we will start first with percent mass. So basically, by its name, percent mass, or in some in some literature, or in some researches, they express it as percent weight per weight, or percent mass per mass. Either way, both are correct. Both are considered, although technically, weight is a different quantity by different quantity mass according to the language of physics. Anyway, so percent mass is just the mass of solute in divided by the mass of solution multiplied by 100. Okay. Now the mass of the solute could be grams, kilograms, or whatever unit of mass that you would like to use. But since grams is the SI unit, we will be expressing mass of solute and mass of solution in grams in this case. Okay. Now, since the mass of solute is now, we have to take note that the unit of the numerator should be the same in the unit of the denominator. So in order for the in order to give a correct, or an accurate value for the percentage. Okay. Now, the mass of the solution, since the solution is just composed of the solute and the solvent, so mass of the solution is just additive. So it's the mass of the solute plus the mass of the solvent, okay? Now, if we have more than one solute, let's say we have solute 1 and solute 2, obviously, the total mass of the solution is equals to the summation of the masses of the two solutes plus the mass of our solvent. Now, going back to our percent mass, so since the mass of our solution is the sum of the masses of the solvent and the solute, so that means the mass of the solute is equals to the percent mass rather is equals to mass of the solute divided by the mass of the solute plus mass of the solvent multiplied by 100. That's it. That's how simple it is. Now, let us proceed to percent volume. Percent volume, sorry, percent volume, just like percent mass, is equals to the volume of the solute divided by the volume of the solution multiplied by 100. Okay, so this is also expressed, some expresses as percent volume per volume. Okay, now unlike percent mass, the volume of the solution is not equal to the sum of the volume of the solute and the solvent. Now, there are some cases that these expressions are equal, but that is not always the case, because depending on the solute-solvent interactions, the solute can either increase the volume of the solution greater to the sum of the individual volumes of the components of the solution, or it can decrease. Okay, that is a case-to-case basis. So how do you get the volume of solution? So this is usually obtained experimentally. Now, there are some questions regarding expressing concentration of solutes that it assumes that the volumes of the components are simply additive. So, well, there are cases like that. However, that doesn't mean that that the volume of the solution is already equal to the volume, the sum of the volumes of the components of the solution. Okay, there are some cases, you will encounter this in some problem solvings, that you assume that all of your volumes are additive. So if that case, that means you use this expression here to substitute here, therefore, which will give you a final equation of the volume of the solute divided by the volume of the solute plus the solvent plus that of the solvent multiplied by 100. Okay. Now, again, I will emphasize, unless stated that you assume the volumes are additive, do not use this expression in obtaining the volume of the solution. Okay? Again, the volume, not all the time that the volume of the solution is equal to the volume of the solute plus the volume of the solvent. Okay? This is really a case-to-case basis. Okay? It depends on how the solute interacts with the solvent and vice versa. So now let's proceed to our parts per million and parts per billion. So now let us proceed with another unit of expression, which is parts per million, or simply ppm. So by saying parts per million is the mass of the solute, or rather, to be specific, it's the grams. Remember, it's the grams, not any other unit of mass, but simply grams of the solute divided by the grams of the solution or mixture. It could be a solution or a mixture, or any other form of homogeneous mixture, multiplied by 10 to the 6 or 1 million. By that, now you know why it is named it's parts per million, because you want to know how many grams of quantities of that solute is present in, let's say, 1 million quantity of that solution. Okay, so it's just simply that. Okay, now there are other units of expression for the parts per million. It could be parts per million or ppm, or in some cases In some cases, in some literature, they express parts per million by expressing it as milligrams of solute per liter of solution. That's it. That is also correct. Okay. Now, this is only applicable when your solution is liquid, ang phase. Okay. So let me correct that. So that means this one can, the amount of the solution cannot be expressed not only in grams but also it can be expressed in ml of solution. So mass. So rephrasing my previous statement, so parts per million is grams of solute per over grams or milliliters of solution of mixture multiplied by 10 to the 6 or 1000. Okay. Or this could be expressed into milligrams of solute per liter of solution. That is, if your solution is liquid, adopts a liquid phase. Okay. Now, if the solution, okay, let me erase this one. Now, if the solution is solid or adopts a solid in a phase, that means your parts per million can be expressed as milligrams of solute per kilogram of your solution or mixture. That can also be expressed that way. So, remember, if liquid ang imo mixture, like for example solution, milligrams per liter. If solid naman ang imo mixture, or sample, that means ang ppm can be expressed to milligrams of solute per kilogram of solution or mixture. Okay? So now, let's proceed to molarity. So simply, molarity is equal to the mass of solute, or rather, sorry, the mole of solute per kilogram of solvent. That's it. Simple as that, okay? Molarity, on the other hand, is equals to the mole of solute divided by the volume of the solution in liter, okay? So that's it. That's molarity. Okay. Now, particularly remember these two because this one will explain. This one will be used as a defining fundamental quantities in determining how the physical properties of our solution changes when you add solvent, which will be discussed later on. Which I will make a separate tutorial video for that. And and also take note of this unit of concentration because among the concentrations that I will be presenting, or as indicated in your outline, this one is the most widely used, or rather the most ubiquitous among those units of concentration that I have shown in my outline. Okay. So now we will introduce another unit of expression, which is normality. So normality is a bit tricky to use, thus it is not commonly known. It is not as famous as molarity as a unit of expression, but nonetheless, this is proven useful, especially when you're doing routine work in chemistry. Okay, so normality is equals to the equivalence of solute over the volume of the solution in liter. Okay, so it's just like molarity, yet unlike it. Okay, so the equivalence is now we have introduced a new unit which is equivalence. Now equivalence is again what makes normality quite tricky to use, because equivalence is equals to the number of moles of the solute multiplied by the number of reacting units, which is in some books is denoted by alpha. So the alpha is a number of reacting units. Now, what is this number of reacting units? Now, the number of reacting units is actually dependent on what the reaction the solute will undergo or usually undergoes. So that is why normality is not commonly used compared to molarity, molality, and other units of expression, because the normality of a solution is actually reaction dependent. Okay, so let's try. So how do we determine what is the number of reacting units or the alpha of our solute? Okay. Wait. Now, it actually depends again on the reaction. So if the reaction is acid-base, or the solution will undergo an acid-base reaction, or it will be used, or the purpose of the solution is for an acid-base reaction, so alpha is equals to the number of H plus or hydrogen cation or hydronium ion or hydroxide ions that it can react with. Now, in pretty straightforward acids or bases, such as acids that already contain an H plus or an OH minus in their formula for bases, OH minus for bases, so that will be equal to the number of H plus or OH minus that the solute in the solution contains in their chemical formula. Okay. So let's take, for example, I'll write it here. Let's take, for example, hydrochloric acid, okay, or HCl. Now, since it is an acid, it will give out H plus cation, okay. Now, how many H plus in HCl is there in their chemical formula? So it is 1. So that means the alpha, or the number of reacting units for HCl, is equal to 1. Okay. Now the unit for for alpha, or the number of reacting units, is equivalents per mole. That is the unit for that. Now for bases, let's say calcium hydroxide. Now, if you see here, calcium hydroxide, by its name, it's a base. So, it will accept H plus or give out OH minus. Now, here, if you can see the chemical formula, how many OH minus does it have? So, it has 2, as indicated by its subscript. So, that means the alpha, or the number of reacting units for calcium hydroxide, is equals to 2 equivalents per mole. Okay? Now, when we discuss about redox reaction, that is again a bit tricky, okay? Because you need to have a background on how to balance what are redox reactions and how to balance it, okay? So we'll have a separate tutorial for that. If the reaction is redox or oxidation reduction reaction, now the alpha for a redox reaction is equals to the number of electrons gained or lost per 1 mole of the solute that undergone oxidation or reduction. Okay, let's have, for example, potassium dichromate. Now, in potassium dichromate, the dichromate anion can be oxidized, can undergo a reduction reaction to produce chromium 2 plus. Okay, so before we determine the alpha or the number of reacting units for the potassium dichromate, we need first to balance the reaction. Okay, so in balancing redox reactions, you balance first the non-oxygen or non-hydrogen elements in the half reaction. So in this half reaction, the only elements present apart from hydrogen and oxygen, or apart from oxygen in this case, is chromium. So we balance first the chromium. So we add coefficient here to balance the chromium both in the reactant and the product side of the reaction. Then after that, we balance the number of oxygens in both sides by adding water molecules. So since there are 7 oxygen atoms here, so we need to add 7 water molecules here. Okay, so I'll just append it this one. Then after that, we balance the number of hydrogens on both sides of the equation by adding H plus. So since 7 times 2, we have 14 hydrogens on the product side and 0 on the reactant side. So we need to add 14 H plus here, which is equals to Then finally, we balance the charges on both sides of the equation by adding electrons. Okay, so here in the reactant side, I forgot to put the charge of dichromate here, which is -2. In the reactant side, we have positive 14 due to hydrogen due to the H plus cations, plus the -2 of the dichromate, which makes it 12, positive 12. Now for the product side, since only chromium gives the charge, and this is neutral, and the water is neutral, so 3 plus, so positive 3 multiplied by 2, so, or rather, positive 6, okay? Now, in order to balance the reaction, we need to add electrons. We need to add electrons on one side here, which is 6 electrons. So that is 12. Positive 12 minus 6 is equals to positive 6, which is now equal to the charge in the total charge in the product side. So this will be our balanced half reaction. Now, based on the balanced half reaction, since the electrons are on the reactant side, that means the product the substance gained electrons. That means this is a reduction reaction. Now, going back to our topic, by the definition of the redox of the alpha, so that means alpha of dichromate in the redox reaction is equals to the number of electrons, which is 6, divided by 1 mole of the solute. Since the coefficient of dichromate here is only 1, that means the denominator here will be 1. Okay? So the alpha will therefore be equal to 6 mole equivalents per mole of dichromate. Now, another way of expressing redox reaction is the change in the oxidation state of the non-hydrogen or non-oxygen atoms that undergone a redox reaction multiplied to the number of atoms. So let's put this trait bars here to indicate that we're only looking for the positive value of the change of the oxidation state. So that means where am I? So multiplied by the number of atoms that undergone the change in that oxidation state. So let's go back to our example previously, which is dichromate. Okay. Now, since we have dichromate here, since we know that dichromate undergoes a redox reaction for it to become chromium 3 plus, so we don't need to balance the whole reduction reaction. We just need to know the oxidation state of chromium before the change in oxidation state and after the change in oxidation state. So this one, the chromium here is pretty straightforward. This is positive 3, its oxidation state. Now, in the chromium in dichromate, we need to get this. So we need to know the rules of our change in oxidation state. So the overall charge is 2, is equals to the summation of the oxidation states of both chromium and oxygen. So we don't know yet the oxidation state for chromium. We multiplied this oxidation state of chromium by 2, since there are 2 chromium atoms present, plus 7 oxygen atoms have an oxidation state of negative 2. So 7 times 2, that is negative 14. Then transpose this on the other side. So 14 minus 2 is equals to 2 Cr, chromium, divided by 2. So your chromium, the oxidation state of chromium in dichromate is positive 6. So I'm running out of board space. Okay, where will I erase this? Dali na lang. So what does that mean? So chromium has an oxidation state of positive 6. So the change is from positive 6 to positive 3. So what will be the change in the oxidation state, therefore? Obviously, this is pretty straightforward. That will be 3. Okay? So the alpha, or the number of reacting units for dichromate, is equal to 3, which is a change in oxidation state multiplied by how many chromium atoms are there in dichromate, which is 2, which is equals to 6 equivalents per mole. This is the same answer that we have obtained if we've used the first method, the first definition of the alpha in the redox reaction. Okay. Now, next up, we will try to develop a connection between the different units of concentration that we have expressed or indicated so far, or we have discussed so far. Okay. So let's have again percent mass. Okay, let's have a percent mass of a solute. Let's name the. Let's say we have let's have let's say we have 0.003 grams of sodium chloride, which is dissolved in 200 grams of water. Okay, so by its nature, percent mass is equals to percent NaCl by mass. Percent sodium chloride by mass is equals to 0.003 grams divided by 200 plus 0.003 times 100 is equals to so plugging in these values will give you a value of 0.0015%. Okay. Now let's say I want to express this in another quantity. Okay. Let's say I would like to express this into another quantity. Let's say parts per million. Parts per million NaCl. Now we need to remember that parts per million is equals to kilograms of solute, milligrams. Milligrams of solute, which is NaCl. And since we don't know the volume of our solution, however, we do know the mass. That is kilogram of our solution. Okay. So so what you just need to do is you just convert the masses obtained here. Okay. Masses given. So let's try to solve this one. So parts per million is equals to 0.003 grams sodium chloride, which is equals to 200 plus 0.003 grams sodium chloride multiplied by 10 to the 6. That is usually the case. Since we are already given the amounts. However, let's say we don't know the amount and we only have percent mass. So let's say we only have going back to our example. We only have percent mass of our NaCl, which is 0.0015% NaCl. So how do we go about that? So remember, percent mass based on this amount. So we can also say that for every 100 grams of our sodium chloride solution, we have 0.0015 grams of sodium chloride. Am I right? So what we just do is we convert the solute to milligrams. We convert this one to milligrams, and we convert the mass of the solution to kilograms. So let's do that. So convert this one to milligrams. Convert the mass of solute to kilograms. So let's do that. Okay. We have 1,000 milligrams for 1 gram, and we have 1 kilogram contains 1,000 grams. So cancel. So we'll plug in our values, and we will get So plugging in those values, we will get, in our calculator, we will get 150 parts per million of sodium chloride. Okay, or for or we have 150 milligrams of sodium chloride per kilogram of the solution or the mixture. Okay, so let's try getting a relation of mass and parts per million from our example. So I repeat, going back to our original formula, percent mass is equals to the grams of solute divided by the grams of solution multiplied by 100. Okay? Now, and since ppm is kilograms of solute, milligrams of solute per kilogram of solution, that means 4% mass. So ppm is also equal to the grams of solute. Convert this to milligrams over grams of solution converted to kilograms. So that is 1,000. 1 kilogram over 1,000 gram. Okay, and based on that, grams of solute over grams of solution is equals to percent mass divided by 100 by rearranging. Okay, by rearranging this first equation, we rearrange this to get this one. And we substitute this expression to here. So therefore, percent mass divided by 100 is equals to 1,000 divided by 1 over 1,000, that is 10 to the 6, which is our parts per million. Okay, so 10 to the 6 divided by 1,000 is equals to, or rather 10 to the 6 divided by 100 is equals to percent mass multiplied by 10,000. So that will be our final equation. To rewrite this, since I'm running out of whiteboard space, the final relation between parts per million of the solute and the percent mass is equals to, parts per million of solute is equals to the percent mass multiplied by 100. That's it. So this is only, again, applicable if the homogeneous mixture is solid. It's ang final phase niya, or ang phase na gina-exhibit sa imong mixture is solid. Okay? So what we have presented so far for the percent mass parts per million relation is if the mixture is in solid phase. What if it's for solutions wherein the mixture is in the liquid phase? So let's have an hypothetical aqueous solution of an hypothetical solute X, wherein its concentration in parts per million is 1,346 milligrams of X per liter of the solution, which is also equal to 1,346 ppm. Now, in this case, we cannot say that this 1,346 ppm is milligrams of X per kilogram of the solution, since we have stipulated here that the expression for the solution in our ppm is in volume. Okay. Now, in order to convert it to mass, to percent mass, we need to know the density of the solution. So let's say the density of the solution here is 1.035 grams per ml of solution. Sorry. Okay. So how do we do that? Now we use this one to convert it to liter. We use the ppm to convert it to percent mass. Okay. Now we have 1,346 milligrams of X per 1 liter, which is basically 1,000 ml. Since 1 liter is 1,000 ml, so we change it to ml, so that we can convert this volume of the solution into grams. So 1.035 grams per ml. And we also need to convert so in order for them to be converted to percent mass, both of them should have the same units of mass. So since this is gram, either we convert the mass of the solution to milligrams, or we convert the mass of the solute to grams, whichever you prefer. Parehas lang na. Okay, so I will prefer that I convert this one to grams. So 1 gram is equal to 1,000 milligrams. Okay, so that will give you 1.346 grams of X is present per 1,035 grams of the solution. Okay, so we have grams of X, we have grams of the solute, and divided by the grams of solution. All we need to do is multiply this by 100. So multiply this by 100, and you get a percent mass of equal to let me calculate this one. So 1.346 divided by 1,035 times 100. So the percent mass of X here is 0.13%. Basically, that's it. Okay. So that is if you have the conversion factor. No. So let's try to create a formula for this one. Okay, based on our examples. So we stipulate that percent mass is equals to the mass of solute in grams divided by the mass of solution in grams. Okay, we have to be very careful with our units, that the mass of the solute and the mass of the solution should have the same unit. Okay, I know I've said this before, but I would like to stipulate this again, because this is one of the common mistakes when you're trying to convert one unit of concentration to the other, and vice versa. And then parts per million is equals to the mass of the solute in grams, and divided by the volume of this solution in milliliters multiplied by 10 to the 6, or 1 million. Okay? So I'll erase this one. So manipulating the percent mass, rearranging the equation, the formula for the percent mass will give you the ratio of the masses of the solute and the solution equals 2% mass divided by 100. Okay? Now, going back to parts per million, ppm is equals to the moles of solute over volume of solution, but since we have been given the density of the solution, which is the mass of solution divided by the volume of the solution in grams and ml respectively. So rearranging this equation, that means the volume of the solution is equals to the mass of the solution divided by its density, right? So going back here, I'm sorry, I'm running out of whiteboard space. So going back here, the volume going back here, we substitute this equation, rather this expression to here. Therefore, not this, to here. Therefore, parts per million is equal to the mass of the solute divided by the mass of the solution over its density multiplied by 10 to the 6th. So rearranging, this could be expressed to mass of solute divided by mass of the solution multiplied by its density times 10 to the 6th. Okay? And since we have shown here that this one is equal to this one, we substitute this expression to here, which will eventually yield to percent mass divided by 100 multiplied by the density of this solution times 10 to the 6th. So the final relationship is that for the ppm, for the parts per million of the solute in the solution is equals to its percent mass multiplied by the density of this solution times 10,000. So that will be your final solution. Okay. Now, in my next topic, I will go directly to the relation of molarity and normality. Between the molarity and normality, I will leave the other interconversions to your discretion. I'll leave you to explore the relationships between, for example, molality and normality, molality and molarity. I'll leave that to you because from what I have discussed here, I have laid out different foundations on how to interconvert from one unit of concentration to the other. I'll leave that I'll leave the others interconversions for you to practice on. So now I'll proceed to the conversion of moles of solute from molarity to normality.
Okay, so forgive me if the audio is of my previous video of the previous parts of or the earlier parts of my videos is really bad. I just realized it nga hindi amo na ka compatible ang akon nga noise cancelling headset compared ang iyang quality sa akon nga laptop. So it's more like it's noise cancelling such that it actually works as the quality of the audio that it receives. Anyway, so let's have this relation. Let's have these units of concentration here. So we have molarity, that is moles of solute per volume of solution in liter, and our percent mass, which is moles of solute, grams of solute over grams of solution times 100. Okay. Now we need a bridging since the quantities of the solutes here are expressed in two different what do you call this? In two different quantities. So we need a bridging quantity there, which is our density. So density of this solution is obviously, by its definition, mass over volume. Okay. Now here, the unit for, let's say the unit here is grams per ml. Now since our molarity is volume, the volume of our solution in the molarity is in liter, so we need to convert that first into ml. So 1000 ml is 1 liter. So you cancel this one, and basically that can be expressed that molarity is the moles of solute per volume of solution in milliliters multiplied by 1000, which is our conversion factor. Now we need also a bridging quantity between the moles between two separate measurements here, which is the moles of solute and the mass of solute, and their bridging quantity is their molar mass. So by definition, molar mass is the grams of solute per moles of solute, right? Because by definition, molar mass is the number of grams of a pure substance per 1 mole of it. So the moles of solute therefore is equals to the mass of solute divided by its molar mass. Okay. So what happens here? Before I forget, rearranging this definition of density, therefore the volume of this solution is equals to the mass of this solution divided by its density. Now, what we do here is we substitute this expression to the moles of solute and this expression to the volume of the solution in ml. What you'll get is the molarity is equals now to the mass of the solute divided by its molar mass all over the mass of the solution divided by its density multiplied by 1000. Rearranging this equation will give you molarity is equals to mass of the solute divided by the mass of the solution multiplied by the moles of solute, molar mass of the solute, sorry, not molar mass, the density of the solute or solution divided by the molar mass of the solute times 1000. Okay? Now, we have seen here that rearranging this equation will give you another expression wherein the ratio of the masses between the solute and the solution is equals to percent mass divided by 100. Now we substitute this expression to here, and what will give you is the final relationship between the molarity and the percent mass. So molarity is the moles of molarity now therefore will be percent mass divided by 100 multiplied by the density of this solution all over molar mass of the solute times 1000, or percent mass multiplied by the density of this solution divided by the molar mass of this solute times 10,000. Okay, let me rewrite this one so that it will be clear. So again, the molarity of the solute is equals to the percent mass of the solute multiplied by the density of this solution divided by its molar mass of the solute times 10,000. Okay? Now this is only applicable when the density is expressed in grams per milliliter, and the molar mass is expressed in grams per mole. Okay, the mass of the solute should be expressed in this case in grams. The same goes with, and the volume of the solution should be expressed in ml or milliliters. Okay. That is the time that this formula is applicable. If that is not the case, you need to convert them to the appropriate value so you can apply this formula. Okay, so I'll end it here for now. Again, I will post more videos regarding our week 8 in our module. So again, don't forget to do more and more practice. Okay, so that's it. See you